Okay, today I'm making another video, a short video for an explanation of Faraday's law. And I'm doing a little experiment here. I'm actually sitting outside at the park in the shade, enjoying the beautiful weather in Berlin. I'm going to try and make this video here laying on the grass right here. And we're going to be talking about Faraday's law, and I'm going to be going over with a simulation. This is really how we talk about generators or generating electricity. And we're going to be using one of the excellent simulations from PHET Simulations. There's their website. Whether you're teaching or learning, check it out. They have excellent simulations for math, sciences, physics, chemistry, biology, all that kind of fun stuff. And we're going to be using this simulation right here. Okay, this simulation has really maybe like 2 or 3 things to it. First of all, we have a light bulb and we have a coil of wire and a voltage meter. The voltmeter is showing the voltage across the light bulb, and the light bulb is connected to the coil of wire. Now you should notice, first of all, it's very important, very interesting, fascinating, that the light bulb is not connected to anything else except the coil of wire. It's not connected to a battery to turn it on. It's not connected to a power supply, a plug. It's not plugged in. It's just a coil of wire and a light bulb. Then we have a magnet. And the magnet has magnetic field lines, which I'm going to turn them on like that. I can turn them off like that. And you will notice, this is the important thing to notice, when I take the magnet and I move it towards the coil, the light bulb lights. When I move it away from the coil, the light bulb lights. When I move it while it's moving towards the coil, the light bulb lights. When I move it away from the coil, the light bulb lights. When I move it back towards the coil, the light bulb lights. But when the magnet is standing still, whether it's here or over here or over here, whenever it's not moving, then the light bulb doesn't light. In order for the light bulb to light, the amount of magnetic field or the magnetic flux inside that coil of wire has to be changing over time. If the magnet isn't moving, then the magnetic flux, the amount of magnetic field inside the coil, is not changing. And you can see it has to change over time. And the faster we change it, the brighter the light bulb gets. You can see if I can move the magnet really slowly, really, I can do that because it's not changing very quickly. It's dependent upon the rate of change, which means the faster I change it, the more voltage will be induced. And this is what we call an induced voltage or an induced current through the coil. And this is how we generate electricity. We have an AC power supply, an AC source in the United States and also in Europe and in most places, of course, except when you're using a battery, that if we move this, you can see we light the light bulb. And the light bulb, if we could move it fast enough, the light bulb would, we could vibrate this like 50 or 60 times a second, the light bulb would stay lit. And you'll notice the faster I move it, the brighter the bulb. If I move it slower, the bulb still lights, but not as much. Because the faster I move it, the lighter, the brighter the light bulb, and the greater the induced voltage. So you can see here, we have the light bulb and the voltmeter, which is showing us the voltage that is being induced in this coil of wire due to the change in the magnetic field or the change in the magnetic flux through that coil of wire. And that is what is called Faraday's law. Whoosh, 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 like that. See that? Just like that. If it's changing over time, you get an induced voltage. If it's not changing over time, which means if the magnet isn't moving, then you don't get an induced voltage. Now, it would be nice, I can't do this with the simulation, but it would be nice if I could take this coil and move it. It doesn't matter whether I move the coil or move the magnet. In either way, as long as they're moving relative to each other, then I can get a magnetic. I can add magnetic field lines so you can actually see the magnetic field lines. All right. I can change the poles of the magnet. Doesn't really matter. You'll notice when I move it in one direction, it goes, the voltmeter goes in one direction. When I move it in the other direction, the voltmeter goes in the other direction. So I go like this, it goes to positive. If I go like this, it goes to negative. If I go like this, positive. I take it out, it goes to negative. All right. But the point is, if If I change the magnetic flux through the coil of wire, then I get an induced voltage. And that is what we call Faraday's law. And this is Faraday's law. Faraday's law says, if you would write it out in words, a voltage will be induced in a coil of wire when the magnetic flux or the field, the amount of magnetic field through the coil changes over time. And this is the equation that we use. The induced voltage is equal to minus. This is the Lenz's law part of the equation. N is the number of coils. This is the change in the magnetic flux over time. And this is how we calculate the change in the magnetic flux. We take the change in the area of the coil. Now, we didn't change the area of the coil, if you noticed, but we did change the amount of magnetic field that was through the coil, and we changed that over time. And the faster we do that, the shorter the change, the shorter amount of time it takes for the change to occur, then the greater the induced voltage, because the time and the induced voltage are inversely proportional to each other. So there you go. I hope you found that video helpful. If you did, please, it means a lot to me, do all of the following 4 things. Subscribe to my channel, get all my excellent chemistry, physics, and math videos. Go down there, give me a thumbs up for this video. Leave me a nice positive comment in the comment section below, and don't forget, sharing is caring. Share this video with all of your friends. Show them just how much you care. Thank you very much for watching. We'll see you in the next video.